Welcome to this VLSI design lecture series. In today's lecture video, I'll be discussing about resettable latches and flip-flops, and especially I'll be discussing about asynchronous reset. As discussed in our previous videos, there are two different kinds of reset: synchronous reset and asynchronous reset. Synchronous reset latch was discussed in our previous lecture video. In this lecture video, our focus will be on asynchronous reset. Asynchronous reset forces Q, that is the output, to low immediately, whereas synchronous reset waits for the clock signal. That's a major difference between asynchronous reset and synchronous reset. Asynchronous reset, the output doesn't depend upon clock. It resets immediately the output to low without the need of clock, whereas synchronous reset waits for the clock pulse, clock signal. So this is the circuit diagram of asynchronous reset. If we observe, the major difference seen in our synchronous reset and asynchronous reset is, in synchronous reset, here we had a tri-state, whereas in asynchronous reset, instead of tri-state, we have a NAND gate. And this particular NAND gate, one of the input is reset bar. Hence, asynchronous reset is independent of clock. Asynchronous reset forces output low immediately, whereas synchronous reset waits for the clock. Let us have a look at its working, how exactly it works. When clock is high, for example, when clock is high and reset is 0, whatever is the D input, for example, here we have D input as 1, that will be reflected as output. Q output will also be equal to 1, this particular latch. For example, if clock is 0 and say example reset is 0, if D input is 0, even if D input is 0, because clock is 0, the previous state 1 which was seen at the output will be retained as it is. When clock is 0 and reset is 1 and D input is 1, the output becomes equal to 0 because reset is high. It doesn't depend upon clock. Whereas in synchronous reset, in previous lecture video, this reset was dependent upon clock. Whereas here, this entire asynchronous reset, the circuit is independent of clock. See here, even if the clock is 0, reset is becoming high. No matter if D is 1, the output is becoming as 0. Similarly, when clock is high and reset is high, if D input is high or low, Q becomes equal to low. So let us verify these conditions one by one. When clock is 1, reset is 0, and D input is 1. Because reset is 0, whatever is the value of D, that should be reflected as output, which is Q. Let us see that. So when clock is high, clock bar should definitely be equal to 0. So this logic level high is given to the gate input of this NMOS transistor, and logic level 0 is given as the gate input of this PMOS transistor. So this transmission gate is completely on. If the transmission gate is on, there's a connection established from this end of the transmission gate to this end. So it acts as a closed switch. Whereas when clock is high and clock bar is 0, this NAND, whatever we see in the feedback section, is off. If it is off, it acts as a open switch. And because reset is 0, reset bar is 1. And D input is 1. So let us append 1 over here. 1 NAND with 1 is 0. So because this transmission gate is on, it acts as a closed switch. So this 0 will be reflected to this particular point. So inversion of 0 is 1. So that 1 will be reflected over here as well. So when clock is high, reset is 0, D is 1, Q should be equal to 1. We are getting that. This is the first case. Let us see the second case according to the truth table. When clock is 0 and reset is 0, even if D is 0, D input is 0, Q output should be 1 because the previous state will be reflected. Let us see that. So when clock is 0, clock bar is 1. 0 is given as the input, gate input of this NMOS transistor, and 1 is given to the as a gate input of this PMOS transistor. So this transmission gate is completely off. The transmission gate is off. It acts as a open switch. There is no connection between this end of the transmission gate to this end of the transmission gate. Whereas when clock is 0 and clock bar is high, this NAND gate in the feedback section is turned on. Now the reset is 0. So reset bar should be equal to 1. D is 0. 1 NAND with 0 is 1. But this 1 cannot be transferred to this end of the transmission gate because this transmission gate is open circuited. It is off. It is open circuited. Whereas previously logic level 1 was present over here, was stored over here previously, previous value. 1 NAND with 1 is 0. So this 0 will be transferred over here. Inversion of 0 is 1, which is the previous state value. Next, let us consider one more case to prove that this asynchronous reset is independent of clock with respect to reset. When clock is 0 and reset is 1, D is equal to 1, Q should become equal to 0 because reset has become equal to 1. No matter what is D, 1 or 0, Q should be equal to 0 because reset has become high. It doesn't depend upon clock signal as well. Let us see that. So when clock is 0, clock bar is 1, 0 is given as the input to this NMOS, gate input of this NMOS. 1 is given to the gate input of PMOS. So this transmission gate is off. It acts as a open switch. Whereas this NAND which is present at the feedback is turned on. Reset is 1. So reset bar should be equal to 0. Now D value is 1. 1 NAND with 0 is 1. But this 1 cannot be transferred to this point of transmission gate because this transmission gate is off. It acts as a open switch. Now, previously one value was stored, which we have already seen. So 1 NAND with 0 is 1. So this 1 will be transferred to this particular point. So inversion of 1 is 0. So no matter what is the input of D, whether it might be 1 or 0, once reset is activated, reset is high, the output becomes equal to 0, which is proved. Similarly, let us see the last case. When clock is high, reset is high, D input is also high. Because reset is 1, Q becomes equal to 0. So when clock is high, and clock bar should definitely be equal to 0. So when clock is high and clock bar is 0, this transmission gate is on, whereas this NAND is off, which is present at the feedback section. Now reset is high. So when reset is high, reset bar is equal to 0. Now the input is 1. 0 NAND with 1 is 1. So this 1 will be transferred to this particular point because transmission gate is on. It acts as a closed switch. So 1 will be transferred over this point. 1 inversion is 0. The output which we get is 0. So when clock is high, reset is high, even though D is 1, because reset is 1, Q becomes equal to 0, which is proved. I hope that you have understood this video lecture. Thank you.